Let me start with this new topic, namely grand canonical ensemble. And I want you to remember that when we talked about ensembles in the beginning, I said that grand canonical ensemble is it corresponds to something called open system. How do you define an open system? You have a system and you have a system, and then there is an environment which we call as a reservoir, kind of a reservoir, or call it as a bar. Now, depending on what is fluctuating in the properties of the system, we can say that it is open system or closed system. So you can see that there is an exchange of energy that is possible between environment, bath and the system. In that, then you have what is called a closed system, or in addition to that, there can also be an exchange of particles. That means your system is not closed. So in open system uh, is characterized by uh, energy, energy exchange, and and particle exchange. Between between the system and the reservoir. Mm. That means we cannot say that number of particles are constant. Just like energy cannot be constant, the number of particles are also not constant. So, but uh, similar to temperature, of the bath that fixes average energy of the system, fixes average energy of the system, the chemical potential of the bath fixes what is called average number of. So, in such cases, you can see that the macro state of the system, macro state, is defined by fixing uh, the temperature, volume, and the chemical. Okay, so, remember in closed systems, we had temperature, volume, and number of. Whereas in open system, number of particles are not constant. So you have to define something called the chemical potential, which is uh, which is fixed. So you can say that system and bath or the reservoir are in equilibrium, when the P and mu are same temperature and same chemical. Now you can understand that if P system is greater than P bar, what happens? Implies there is a directed flow of energy from system to bar. High temperature to low temperature, the energy will spontaneously get transferred. In the same way, if new system is greater than new bar, that implies there is a directed flow of particles, flow of matter or particles, matter from system to bar. So the equilibrium will get established. We cannot say that when T system is equal to T bar, uh, we cannot say that there is no transport. So if T system is equal to T bar, okay, so we cannot say that there is no energy transfer, energy exchange between system and bar, but we can say that we can say that there is no net transfer, net transfer of energy from one to the other. A similar remark can be made with respect to chemical potential. A similar remark is applicable in case where mu system equal to mu bar with respect to exchange of matter. There won't be any net exchange, but there will still be exchange. Okay, so now we can say that this so the situation is somewhat like our previous previous closed system, that is canonical ensemble, except that here, in addition to energy being exchanged, you have also a number of particles. Okay, so now what happens is that you have our approach is somewhat similar. We will assume that the composite system of system and bath system and bath is an isolated system with energy, let's say E0, and number of particles, say mg. Now you can ask a question that a microstate of a system, a microstate system now depends on two things. System has a particular energy, which I can call it as Ei, and a particular value for the number of particles. It's called as some mg. So the task, our aim is in this particular case. So our aim is to find the probability of a microstate of the system whose energy is Ei and number of particles is constant. So this is our aim. Just like we had the aim in closed system, our aim was to find out the number of probability of a microstate of the system whose energy is Ei. There the number of particles are fixed, but here since that also can vary, so we would like to ask the question. Now, let me not repeat that argument, but I hope you will be able to understand if I write. If I ask P of Ei, comma Nj, P of Ei, comma Nj is proportional to the number of microstates of the bath corresponding to an energy given by E0 minus Ei and the number of particles given by n0. Because if the system has got an energy EI, then bath will have got an energy E0 minus EI. The system has got a particles Nj, and the bath will have N0 minus Nj. The total number of particles of the composite system, as I have written here, the composite system of system and bath, it has got an energy E0 and then the number of particles. Okay, so this is proportional to this, and I am able to write this, remember, because this is an isolated system, and then all microstates of this isolated system are equally common. So this probability will be proportional. So I can write this. As exponential of 1 over AB, the volume constant, into entropy of the bath with E0 minus Pi, N0 minus P. So bath is a large system, and so since EI is much smaller than E0 and Nj is also much smaller than N0, I can actually expand this in Taylor series around. I can write down as B of E0 minus Pi, comma N0 minus Nj. I can expand it around E0 and N0, which will be given by B of E0 comma N0 plus the partial derivative of SP with E evaluated at E is equal to E0 and N is equal to N0 into minus Pi plus now we have two variables. So this is SP divided by N evaluated at E is equal to E0 and N is equal to N0 into minus Nj plus you have other higher order terms. So I can neglect these higher order terms because this EI and Nj are very small compared to N0. And note from thermodynamics, from thermodynamics that 1 over T is equal to SB by E. Of course, this is temperature of the bath, but temperature of the bath is same as the temperature of the system because they are in equilibrium. So you can say that this is same as the common temperature. Similarly, you can write down OSB by rho n as mu by, I guess it is minus. So even though this is mu d by Td, but since because of equilibrium, the system and bath are in equilibrium at temperature P and total potential chemical potential. Then I can write down that so I substitute this one. This is some constant. So since I am only talking about proportionality, I don't have to worry about this constant. So I can write down that P of Ei comma Nj is equal to, I can write down exponential of 1 by kb times I have minus Ei by t plus mu Nj by t. So this is sorry, I think I must write this as this proportionality. So this is, I can use this as exponential of minus beta ei. Okay, so I can pull out beta ei minus mu times mg, exponential minus beta ei times. So this particular factor is called Gibbs factor. Remember, e to the minus beta ei is called Boltzmann's factor. So this is called Gibbs factor. Now, how do I fix the constant of proportionality? It is again the same logic. So what we can do is that we say that when you take sum over I and then sum over k, we take p of pi comma nj, that has to be equal to the total probability when you sum over all the microstates have to be equal to 1. This implies I can define some quantity called Q, which will be a function of temperature, volume, and the chemical potential, which is given by sum over I and sum over k e to the power minus beta into ei minus mu n. Okay, so this particular so here the sum is over all microstates. All microstates, independent of the fact whether they have same energy or same number of particles, list all the microstates and take sum over all microstates. Okay, so if you do that, this particular quantity is called grand canonical partition, or sometimes we call it as simply grand partition. Okay, so now there are two things that we would like to do. So that in terms of that, what happens to the probability of a microstate? So we can write can now write the probability of a microstate with an energy EI, number of particles as in J, is equal to 1 over Q into e to the power minus beta of EI minus mu. So this is something like our canonical probability distribution. It is called grand canonical probability distribution. Okay, so now in terms of various quantities, now remember this. So here our macro state is so it is a function of a grand partition function is a function of t, e, and tvn. So if you go to thermodynamics, there is something called Helmholtz free energy. Okay, so F, which is a function of T, E, and N, which is equal to U minus Ts. Correct? Now I want potential which depends on T and mu. Okay, so remember that this implies your dF can be written as du minus Tds minus sdt, which is equal to Tds minus Tdv plus udn minus Tds minus sdt. Okay, this we have seen earlier, but I am trying to show you that when you take a differentiation of this with respect to n, you will get chemical. So, if you want to make a Legendre transformation, okay, so you can take f of q, v, and n, and then go through a Legendre transform. To a potential, I will call it as some phi, which is a function of t, v, and mu. And how this will look like? This is f minus, this is the Legendre transform, the slope dou f by dou n. Correct. So now you can see that f. So this is nothing but f minus mu, f minus. Correct. So that means if you are asking what is d phi, equal to df minus mu dn minus n dE, which is equal to minus sdt minus pdv plus mu dn minus mu dn minus n du. So which is equal to, I have this mu dn cancelling with each other. So I have minus sdt minus pdv minus n du. So in terms of this potential, I can write n equal to minus So phi. So this is what gives rise to average number of stars. Okay. So if we have some thermodynamic potential, if your control parameters are temperature, volume, and chemical potential, then there is a thermodynamic potential called phi, whose minimum will determine the equilibrium. So this I can obtain from here, from the Helmholtz free energy. Now what we have to do is we have to see that it will be so you can see that if you have the grand canonical partition function. So what is our job? We have to now relate. We have to now relate this potential phi and grand partition potential phi and grand partition. Now let us look at this thing that you have. We can write this mu n to be the Gibbs free energy. And write mu n to be Gibbs free energy. And you know Gibbs free energy can be written as F plus P. In that sense, you can write down this phi to be F minus G, which is equal to minus P. So minus PV is the potential that we are talking about. So similar to what we had in canonical partition function, we can say that this phi, the grand potential, whatever this potential, can be written as minus kBt logarithm of. Because remember, this phi will depend on PV and mu, which is equal to minus kBt logarithm of Q also depends on PV and mu. Okay. Now you can see that, but phi is basically minus PV as we have seen here, and therefore we can say that for grand canonical partition function, PV by KT KBT is written as logarithm of. So this is the relation to thermodynamics. This is the relation to thermodynamics, and you can see that same kind of relation, like I have the average number of particles, as you can see, is minus rho phi by rho mu, and phi is equal to minus kBt logarithm of z. So I can write down this kBt, or I can write down. Okay, let it be like this. So dou by dou mu of logarithm or average n by kbt, average n by kbt is equal to dou by dou mu of logarithm. So I'm just mentioning these two because if you find out the grand canonical partition function, that is q once, then you can relate it to PV by KT and this one. So you can see that the right hand side is a function of, okay, so this is a function of mu, function of mu, and similarly this right hand side is also a function of mu, function of mu. Now between these two equations, if you can eliminate, okay, so by eliminating the chemical potential between these two equations, namely PV by kBT is equal to logarithm of Q, and N by kBT is equal to rho logarithm of Q by rho mu. We get what is called the equation of. Okay. So equation of state is very important for any system. So equation of state determines the equilibrium properties of the system. So getting an equation of state is one of the main criteria, or one of the main aims of doing statistical mechanics of an system. So you write down grand partition function, and then you can get equation of state from these two, eliminating mu between these two cases. So we have written down a formal expression for the probability of a microstate in grand canonical ensemble, and then defined the grand canonical partition function. And now we have related the grand canonical partition function to thermodynamics. So these are the three things that are that we have done so far. But we must also understand how to calculate this Q for a given system. Okay, so let's there is calculation of the function. Okay, so this is something which is important, and so you notice that you have. So I want you to recall we had looked at some problem earlier. So I want you to recall this picture that you have. So let's go back, recall this result. We had 10 spin half particles and spin half particles in magnetic field in D field. So such a thing we had. Then I wrote down if you have only one particle, then you have only two microstates associated with that. If you have two particles, then you have four microstates associated with that, and down. And if you have three particles, there are 8 microstates. Okay, so this is up, down, up, down, up, down, up, up, down, up, uh, down, and you have n is equal to 4, n is equal to 5, etc. And you remember that that time we said that all these microstates are accessible. Since n is not fixed, all these microstates are accessible in grand canonical. Okay, so these are accessible microstates. Microstates for an open system. The open system number can change for an open. Now, if you look at our grand canonical partition function, look at Q, which is equal to sum over I and sum over j e to the power minus beta into ei minus e and j. Now you can see that I can do one summation. I can do one summation and then leave the other summation intact. That is summation over j. Summation over j is on the possible number of particles of all the microstates. Okay. So I can define a quantity. I will call this as this small z, which is equal to e to the power beta infinity. Okay, and this quantity has a name. This is called fugacity. This is called fugacity. Now we can write this Q in terms of fugacity in the following fashion. I can write down Q is equal to sum over j. I can write this as j to the nj, z to the nj into sum over I to the power minus beta. Yeah. So now you can see that this is sum over all possible numbers, number of particles. Okay, but you can understand if you look at this table. I have one particle, I have two particles, I have three particles, and so on. So how many microstates are there in one particle? There are two, here there are four, here there are eight, like that. Okay, so I can say that now if the number is fixed, okay, if the number is fixed, then this entire region will become accessible microstates for accessible microstates for a canonical answer, as the number is fixed here. Correct. So because of that, I can write this summation in a slightly different way. I can write this as Q is equal to, so instead of writing a summation over some j, I can say Q is equal to, I can start with sum over n, which runs from 0 to infinity. That means no particle, one particle, two particle, like that. And each one of this will have a factor fugacity raised to the power n, and then the remaining is only this. Okay, remaining is only this, and that is essentially our canonical partition. That is Z, T, V, and okay. So this is canonical partition function. canonical partition function for n part. But we don't have, now for each n I have a different partition function. Then imagine that z, so I will forget about this t and v because that is same for this q also. So let us say z, z0, z1, z2, etc. some zn and so on. If you see this, this is like a sequence of canonical partition function. Canonical partition. Now, whenever you have a sequence of canonical partition functions like this, and then you write down thing like this, what can you say about this Q? Okay, so let me just remind you that suppose you have P0 of x and P1 of x. Let's say some PL of x. These are sequence of Legendre polynomials. Okay, sequence of Legendre polynomials. Okay. Now suppose if I write sum over L is equal to 0 to infinity, some t to the power L into PL of x. Suppose if I ask what is this, okay, this will converge to some function, right? So that function is 1 minus 2tx plus. So what do you call this function on the right hand side? We call this a generating function, right? So it is very nice that the grand canonical partition function. Okay, so notice that that the grand canonical partition function is a generating function, of a sequence of canonical partition functions, for uh, different number of particles, or for different particle numbers. I think that is the right way. Different particle numbers. Okay, so that is nice. So this gave a very nice way of calculating this. What is the advantage of this one? Now calculations become very simple. Okay. For example, let's say that we want to let's look at an example. Find grand canonical partition function of the classical ideal case. canonical ideal. Now I'm sure you have at least calculated this z as a function of a, v, and n. You know is equal to 1 over h power 3n into 1 by n factorial. This is for the Gibbs paradox, and integral dq bar into e to the power minus beta h of q bar p bar. Okay, so for ideal gas, it's a classical non-relativistic ideal gas. So h of q bar p bar is sum over I is equal to 1 to 3n pi square divided by 2. These are all free particles, and hence you can write this as z of Vn is equal to 1 over h power 3n into 1 by n factorial, and positions are just integrated, give you a volume, and then I have minus infinity to infinity dp e to the minus beta t square by 2m. So this I have to raise it to the power 3. Okay, so this is, so we have seen that this kind of an integral with this h power 3n will be v to the n divided by n factorial into a quantum volume raised to the power n. Okay. Quantum volume raised to the power n, where you can see that this VQ, this will be basically a function of temperature. So now you have this partition function. Now to write down what is grand partition function. So grand partition function will be a function of T, V, and the fugacity Z. Instead of mu, I am writing this Z. That's equal to sum over n is equal to 0 to infinity z to the power n, and I have to write down this v to the power n divided by factorial n into vq to the power n. So I can write this in the following fashion, that is n is equal to 0 to infinity. So let me write down zv by vq raised to the power n divided by n factor. So what this is some x to the power n by n factorial from n equal to 0 to infinity is essentially exponential of z v by v. So you can see that it is so simple that the grand partition function for PV and Z is equal. Okay. So as I told you that if you, it is very simple once you know the canonical partition function, obtaining grand canonical partition. Now we have written down. We have written down. So we know that let's say PV by KT, PV by KBT is given by logarithm. Correct. So logarithm of q, that means it is equal to z v by v. So this is one equation, and then I have average number of particles by kbt is equal to dou by dou mu of logarithm of. But I would like to write this as dou by dou z in terms of fugacity of logarithm of q into dou z by dou mu. Okay, so what that is, remember that z is equal to e to the power theta mu. So dou z by dou mu is equal to e to the power theta mu into b. Correct? So that is nothing but beta into z. Correct? So we have so now you have average number of particles divided by kbt is equal to beta z into dou by dou z of logarithm. But this beta is 1 by kt, so there is a 1 by kt here. So this 1 by kt and this 1 by kt will cancel. So you have average number of particles is simply z dou by dou z of logarithm. So that is given by z dou by dou z of logarithm of q is zv by v. So that will simply give you z v by. Now I have this relation, that is average n is equal to z v by v. So what does that mean? That means this zv by vq on the right hand side can be written as n. So you have pv by kbt is equal to average n. And this is the equation of state for ideal gas, that pv is equal to n. So when I wrote down earlier that you have to eliminate mu, in this case mu means z, to obtain the equation of state. Ideal gas is a simple case, so I will be able to eliminate z and get a simple equation of state in the case of ideal gas. So this is one example where I can easily show you that this kind of a grand partition function can be easily calculated. Okay, so now it is interesting to see that there are some problems where the grand partition function, grand canonical ensemble, is more instructive to work with than the other ensembles. Okay. So one of the problem that we can look at is there is something called um, absorption desorption problem. Absorption desorption process. So the model that we are going to look at is you have a some kind of a chamber, and then there is a kind of a solid. So it's a crystalline solid, and then you have some gas. Some gas. Now what happens is that some gas molecule can adsorb onto the solid matrix, or some solid atom from the crystal can dissolve into the gas phase. Okay, so when there is a transfer of particles from this phase to this phase, we call that as adsorption. Adsorption. And if there is particles that are going from solid to gas, then we call it as desorption.
Sir?
Yeah.
So what is the difference between desorption and sublimation?
Sublimation is a kind of a phase transition, but this adsorption and desorption is not a phase transition. Okay. Sublimation is a solid phase becoming a gas phase directly. So there is a phase change. That means in sublimation what happens is there is no solid that will remain. But here this adsorption and desorption happen only on the surface. In the interior of the solid there is no change. Okay, in sublimation all the solid will become gas. Okay, so but notice one thing, that why we are coming to this the grand canonical picture here is that the number of particles in either the gas phase or the solid phase are not constant. So note that n is not constant for gas as well as solid. Okay, that is why if you consider any of the system, it is like open system. Now we don't want to do too much of calculations, but just understand the concept. Let me make my model slightly simple. So the model is that I'm going to consider this vapor, or what we call as gas. I'm going to model this as an ideal gas. Okay, we're going to model this as an ideal gas. And then the solid is there. Okay, so I'm going to, and solid is basically a crystalline solid. Okay, so I'm going to model this as Einstein solid. What is Einstein solid? Einstein solid is the one for which the excitations are like Einstein's model excitations, thermal excitations. So I'm going to consider this so that I can do calculations easily, because these calculations we are already familiar. So for the ideal gas case, we have already just now done this calculation. So let me say that the grand canonical partition function of P, and N. Okay, this is for gas or vapor. So for this vapor, let me do this calculation. This we have already done. That is V to the power n divided by factorial n. Now, just to tell you that the Vq to the power n is the one that depends on the temperature. So let me simply write that as some function of temperature, where this f of t is 1 by f of t raised to the power n. That means this f of t is simply 1 by Vq, which is nothing but 2 pi m kBT divided by h square to the power 2g. So this is a function of temperature, and we're just going to call this as some of that. Then the grand canonical partition function, so GCPF for this one is the generating function, so PV and Z, which is equal to exponential of Z V into F. Correct? So I may have to write this as Vg here because this is the gas volume. Okay, so let me use that. Now the average number of particles, so let me call this as 10g, is given by Z dou by dou Z of logarithm of 2, which is given by, let me also call this as Zg. I will write that at the end. This is equal to Z G into G. Or in other words, I can write this Zg, it is viscosity of the gas, is equal to Ng divided by Vg into F. Okay, so this is what I have for the figure. Now let's look at Einstein solid. So you can see that for the solid phase, you can see that my PV and N is going to be sum over some small n is equal to 0 to infinity e to the minus beta h bar omega into n plus half. These are the eigenvalues of harmonic oscillator. So this is this one, and this is for one particular oscillator, and then raise this to the power of n, if there are n. So this is something which you can see that I pull out e to the minus beta cross omega by 2, and then I have remaining as sum over n is equal to 0 to infinity e to the minus beta h bar omega raised to the power n. So this is a geometric series, and I get this as e to the minus beta h cross omega by 2 divided by 1 minus e to the minus beta. Now I take it to the denominator, then I can write this as 1 by 2 sine hyperbolic of beta h cross omega. This is a function of t, so let me call this. So what I have evaluated is simply Z1, one oscillator, Z1 to the power n. So I will simply call this as 1 by some phi of. Okay, this is a function of temperature. I'm just calling it as phi of t, where this phi of t okay, so we simply call this as phi. Okay, so where phi of t is given by 1 by 2 sine hyperbolic beta h cross omega Okay, so if this is canonical ensemble, canonical partition function, then the grand canonical partition function, is given by Q is equal to sum over n is equal to 0 to infinity, set to the n into phi of Q to the n. Okay, so that is equal to sum over n is equal to 0 to infinity z into phi of Q to the power n. So this is again a geometric series, and then you have 1 by 1 minus z into phi of. So Q for the solid phase is given by 1 minus z into phi of Q. So suppose now I want to write down what is the average n. Okay, so n in the solid phase, that is equal to z divided by z into logarithm of Q. So that's equal to z divided by z into there is a minus sign, so I will put the minus sign here. Logarithm of 1 minus z into phi. So that gives you minus z into 1 by 1 minus z into phi of t into minus phi of. Okay, so that gives you z phi of t divided by 1 minus z. So I would like to find out what is z. So you can write down. So to find capacity of solid phase, solid. Let us write down this n solid into 1 minus z phi of t is equal to z phi of t. So I can take it on the other side. So z phi of t into this ns plus 1 is equal. Or in other words, you can write down that z of the solid phase is equal to ns divided by ns plus 1 into 5. Okay, so this is an expression, but note that usually ns is a very large number, definitely a very large number compared to 1. So ns plus 1 is same as. So under this condition, this Zs is simply 1 by 5. Okay, so now we have two expressions, namely, so we have gas and then solid, and for the capacity for the gas, that G is equal to Ng by Vg into F of T, whereas Zs is equal to 1 by 5. Okay, so now we ask the question, when there will be equilibrium between these two phases. That means we will have no net absorption or disruption will have no net absorption or desorption if the fugacities are equal. If that gas is same as dead solid. So when that will happen? That will happen when these fugacities are equal. That means your Ng by Vg to f of t should be equal to 1 by 5. In other words, this implies we have Ng by Vg is the number density of the gas should be equal to f of t by 5. Now the right hand side is some function of temperature. Okay, some function of temperature. This is a gas density. Now you can see that for a fixed value, suppose let's say you fix the temperature. Okay, so for a fixed value of temperature, the right hand side, namely this f of t by phi of t, f of t by phi of t is fixed. Okay. Now if your gas density is such, the number density of gas is such that if this Ng by Vg is greater than this number, this fixed value, so f of t by phi of t, suppose if this is greater, then what happens? Then there is a net absorption. That means there is an absorption domination to be there. Net absorption. On the other hand, if your Ng by Vg is less than that, if it is less than that, f of t by phi of t, then uh, then net desorption takes. Net desorption takes. There won't be any net absorption or desorption if Ng by Vg is equal to f of t. Now you can also visualize this in a slightly different way. For example, let's say that we can also see like let's say that let us fix the gas density. Let us fix Ng by Vg. Okay, such that you fix it such that fix it in such a way that Ng by Vg is greater than f of t by phi f. Then what happens? There will be more adsorption. That means this is adsorption dominant condition. Now let's say that you increase the temperature. Okay, so now increase the temperature. Now as you are increasing the temperature, what happens is your this factor increase the temperature, then this f of t by phi of t increases. Okay. And at some temperature, at some T is equal to, let's say, some T star, we 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 have situation that Ng by Vg is equal to f of T star by phi f. Okay. Now, if you further increase the temperature, so on further increase of T beyond T star, then this option done. So you can also determine what is the temperature at which there is no net absorption or diffraction. So essentially, the idea is very simple. The idea is we are trying to uh, establish some kind of known absorption desorption condition by simply equating the gas phase. And this is a generic procedure, but we have used this simple problem because this we can calculate things easily for this. And the idea is very uh, very simple, but I think you will be surprised that we have used this idea and published a paper in 2020 for one of the experiments that was done in our department. So there was an experiment done in Suraj Sinha's lab, where they had a plasma in contact with metal, and they have this kind of IV characteristics of something called laminate probe. So they had observed certain experiment and experimental results. So I was they have shown me those results, but I have made this calculation considering set of electrons in the metal as Fermi-Dirac gas and the electrons in plasma as a Maxwell-Boltzmann gas, and then calculated the fugacities of each one of these systems, and then assumed that there should be under the experimental conditions. I have shown that there is a net transport of electrons from plasma to the metal, and that actually results in the observed IV characteristics. So why I am saying this is that the seemingly textbook-like calculation, depending on the system, sometimes you do the same calculation because system is somewhat at a research level. Even simple calculations can give rise to some publishable results. So this is one. Actually, I did not do anything more than this calculation, but only the systems are different. Here I used a model of Einstein solid and gas. There the model was Fermi-Dirac gas and then Maxwell-Boltzmann gas and electron. That is the only difference. So mathematics will be different, but other than that, the concepts are exactly like what I have discussed. So I will stop here. If there is any question.
Hello, sir.
Yeah.
So I didn't understand the part that we will have no absorption or desorption at when the fugacities are constant, they are equal. But
Yeah.
from what I know that It should be the rate of change of the number of particles should be zero. Like dns dt equal to dng dt equal to zero.
Correct.
Rate of change of number of particles should be zero at equilibrium,
Yeah.
isn't it?
Yeah. Yeah. So I'm not saying that there is no absorption or desorption anywhere. If you carefully, I always use uh, this phrase called net absorption. Okay, net absorption means there is no directed transport of particles from solid to gas. Okay. So here also I see I have used this word called there is no net absorption. Okay, so that is same as what you are saying, that there is no directed transfer, but there will be some absorption and desorption that is taking place, and there is some steady state that we will definitely get. It depends on, of course, the rate of absorption and desorption. Uh, but once the rates are fixed, then there will be some steady state. That there won't be
So,
any net absorption.
sir, what is the relation between fugacity and rate of change of particles? Like,
Um, so basically, it is like if you if it is the rate of change of particles in one system is suppose let's say we have only two systems. So if there is a rate of change of particles in one system, the rate of change will be same as in the other system. If there is uh, if there is no net transport, right? For example, if you say that we have two systems, let's say system one and system two. So the particles, if there is a decrease in the particle, it should go here. If there is an increase in particle, it should come from here. So like that, let's say. So what happens if the fugacity of this system and fugacity of this system are different? So let's say Z1 is greater than Z2. Okay, so then there is going to be a transport in this direction, a net transport in this direction. Okay, so that when you are trying to ask what is dn1 by dt, dn1 by dt, so this will be less than 0. And by dt, dn2 by dt is basically both will be 0. There is no net increase or net decrease in the in this case. In some sense, the rate of change of particles is an effect, and chemical potential or fugacities is like cause. So that is the relation. The chemical potential gradient will drive the particle transport.
okay, sir, thank you.
Excuse me, sir.
Hmm?
Sir, first you mentioned that if chemical potentials of the two systems are same, then there will be no net transport, right?
Hmm. Hmm.
But now you are saying if fugacities are same, then there will be no net transport.
Yeah, yeah. So fugacity and chemical potential, I am using them interchangeably here. But of course, there is that means that I am now talking about same temperature. So fugacity has got both temperature and chemical potential in that. Okay, so if I agree to not to change the temperature, then I can talk about them interchangeably. But if I am varying temperature also, then I have to be careful in using this language. But let's assume that we have fixed the temperature and we are not going to change it. In such case, I can talk about chemical potential and fugacity in an interchangeable manner. Because for a fixed temperature, the relation between fugacity and chemical potential is a monotonic relation. It is an exponential function.
Yes, sir. Yeah.
What is that? You have some courses in theoretical physics as your title.
Oh, I mean, I just mistakenly log in with this ID. I mean, I don't know. Sir, I have a doubt regarding previous, I mean, one of the previous class. Sir, while we are taking the particles of the system to be non-interacting, and there are some discrete levels. So we are talking about probability of finding a particle in a particular energy, right? That's what you did in solving problems. Probability of finding a particle in a particular energy. But
Yeah.
but initially, while we derived the formalism, we asked what is the probability of finding the system in a particular microstate.
Correct.
So how these things are linked?
So the idea is something like this. If you uh, your microstate is that of all particles. Okay, particle one is in some energy state, particle two is in some energy state. So now you consider all the n particles and then write down the energy of that n particle state. Okay, then you can get a microstate. But I can also, if the particles are not interacting, that means one particle does not know the existence of the other. So this particle can be in any one of the states that are available for this particle, independent of the fact whether the other particles are in that state or not. As long as there are no quantum many body effects. If quantum many body effects are there, then you have to respect the symmetry properties of the many particle wave function. But if we are well within the classical statistics region, then it doesn't matter. So you first find out for one particle what are all the possible states that it can be there. Essentially, find out the partition function for single particle, and then raise it to the power n to get the partition function for all the particles. But we have to always keep this in mind as a caution that this can be done only if they are non-interacting particles.
Yes, sir. Sir, the partition function can be obtained from from a single particle partition function.
Correct.
But I am talking about the numerator. In numerator, you always have a particular microstate. So, but I mean, while
Oh, okay. You're asking when I'm writing the probability, how do I do it?
yes, sir, yeah.
Uh-huh.
That part
So
you explained yesterday. I mean, in the previous class. Yeah.
that is when we are doing the two-level system. That time
Yes,
we.
sir. Yes, sir. Yeah.
So I have to differentiate two things here. Namely, let's say I have a probability of so let's look at this concrete example. We talked about the ground state and excited state is WB generated, right? So let's say
Yes,
that
sir.
I take this particular microstate. Okay, so I ask probability of the microstate rounded. Okay, that microstate's probability I want. So I said this has zero energy and this has epsilon energy. So this is equal to e to the power minus beta epsilon divided by 1 plus 2 times e to the minus beta epsilon. So the denominator is the partition function.
Yes, sir. Yes, sir. Yeah.
Correct. But now
Yes,
I
sir.
can in the rounded one in the excited state. That means excited state involves this one as well as this one, right? So in that case, I have to write down the probability as 2 into e to the minus beta epsilon by 1 plus 2 into e to the minus beta. Basically, probability of this one plus probability of this one. That's all. So whether we are going to talk about probability of energy or probability of, so this one corresponds to probability of the energy being epsilon. This is probability of microstate. Correct? So that is the difference between these two. So in the problem that I have done earlier, I was only asking what is the occupancy of excited state like that. No. So there I was only interested in particle in the excited state. So in that case, I have to put in the degeneracy factor here. Okay. So if I am using this probability of one of the microstates, then whatever we discussed earlier, we have to use just the Boltzmann factor for that particular microstate.
Sir, first you wrote probability of one of the microstate, right? At first, the probability of microstate rounded. So is it the microstate of the system? Because you are just talking about state of a particle.
This is just a single particle. Okay, this is the microstate of a single particle. So all this discussion is for single particle. Okay, and this discussion is valid because they are non-interacting particle. We talk about one single particle and then do the same thing for n number of particles. Raise it to the power n.
Okay, sir.
Sir?
Yeah.
So is there a relation between fugacity and principle of detailed balance? Because the change of particles are the same. Rate of change of particles are same if the fugacities are the same.
Basically, one can show that if you use principle of detailed balance, okay, you can get an expression for the probability which is same as the expression that we have written in terms of the Gibbs factor. That is, you write down principle of detailed balance, and then you can get an expression for the ratio of probabilities. So there, the probability ratio will be simply ratio of the Gibbs factors.
Okay, sir.
Okay, so if there are no questions, then we can close. So is there some decision on the exam?